We start in the middle of an active incident response. An intrusion detection system begins reporting a massive spike in suspicious activity. The sheer volume of the anomaly is the first red flag. 26 critical threats are appearing in real time, and 13 of them are originating directly from the user's local machine. Compromise indicators begin with aggressive outbound port scanning to external targets. These IPs map directly to Azure machine learning servers and GitHub content delivery networks. Another severe indicator appears: shell command execution over large UDP packets. The captured hexadecimal strings reveal complex data structures. Observe that this payload contains stack-based exploit patterns. Specifically, the FFD4 sequence translates to an indirect function call, a method used to jump to malicious code in memory. Despite these signatures, an endpoint scan confirms the local system is entirely secure and isolated. No external malicious binaries or recognized supply chain Trojans are executing in memory. The traffic's origin becomes clear by tracing network calls to the application layer. The process generating all 26 threats is code.exe, Visual Studio Code. We have to deconstruct this packet log to see how modern developer telemetry has become behaviorally indistinguishable from malicious data exfiltration. To solve the paradox, we begin with protocol attribution, analyzing exactly where this outbound traffic is trying to go. The local machine is initiating port scans over port 443, specifically targeting Azure's automated threat detection infrastructure. The traffic is bidirectional and reactive. Microsoft's machine learning models are actively responding to the IDE's probes with a secondary wave of data. Moving up to the process layer allows us to identify the exact origin point of these calls. In a forensic investigation, network socket connections are mapped back to a specific process ID to find the software responsible for the traffic. The logs confirm that process ID 10388 maps to openconsole.exe, a subprocess of the VS Code terminal. At this stage, most developers assume this is just normal GitHub repository synchronization via Copilot or built-in Git tools. But the environmental data shows a critical discrepancy. The user has no active Git repository open. Without an active repository to sync, code.exe is initiating unsolicited, highly aggressive connections to remote infrastructure, moving data between the local machine and the cloud without any user-initiated trigger. We move to payload deconstruction, diving directly into the encrypted packets intercepted by the network monitor. One specific signature triggered the system alarms, the hexadecimal string 6A0B. This maps to the assembly instruction push 11, a command used to prepare an operating system for code execution. The logs also captured the string 8-9-E-3. This represents the instruction MLV EBX ESP, a classic register setup used exclusively for memory manipulation and function calls. To understand why these patterns are here, we have to look at the execution context. These assembly patterns are being emitted across the network. They're in transit, not actively executing on the local machine. This is a massive departure from standard HTTPS telemetry, which typically consists of benign JSON files or plain text. Finding raw, uncompiled assembly instructions wrapped in a secure tunnel violates the standard rules of application telemetry. From the perspective of a network monitor, this behavior represents deliberate shellcode tunneling and active code injection. Visual Studio Code is smuggling executable shellcode out of the local environment, delivering it to Microsoft's machine learning servers. To find the source of these payloads, the investigation moves from the network packet back to the local hard drive. We look at the directory path where code.exe was operating, a folder named Network Scanner Defense. This workspace belongs to a security researcher developing custom Python scripts for intrusion detection. Inside this folder is a single document, cli_security_interface.py. This Python script contains literal, hard-coded arrays of shellcode strings. They are used as reference signatures to help the program identify malware. When this directory is opened, Visual Studio Code automatically indexes the entire workspace to power its code intelligence features. The IDE's indexer harvests these malware signatures directly from the code files. The software packages these extracted signatures, wraps them in HTTPS, and transmits them to Azure for Copilot training. The intrusion detection system worked perfectly by catching shellcode on the wire, but it generated a false positive because it had no way of knowing the IDE was performing an unprompted data exfiltration of its own workspace. Recent updates have integrated automated data harvesting directly into the core functions of the IDE. Features like code intelligence quietly scan and transmit entire local workspaces without requiring user permission or a connection to a remote repository. This operational reality breaks legacy, signature-based security models. Local firewalls cannot differentiate between an IDE's background telemetry and a malicious actor stealing intellectual property. Vendors wrap this telemetry in complex encryption to bypass basic anomaly detection, even as they intentionally trigger deep packet inspection tools. In the era of cloud-assisted development, allowing a binary like code.exe onto your machine implicitly grants permission for complete workspace extraction. Network perimeter defense based on static signatures is obsolete because the tools we use to write code are now designed to smuggle those same malicious